In this chapter, we will talk about convective heat transfer. Now, we have done conduction heat transfer, and that was for a solid or the medium was not moving. Now, in this chapter, we're going to study heat transfer in a fluid where the medium is moving. Now, all of us have experienced this in the hot days that you turn on or turn up the fan to cool down. When we do not have a fan, like this picture here, we still need to lose heat because we keep generating it. So how much heat we lose in either case, here or here, matters in our thermal comfort. But the mechanisms of losing heat is different. So in this case, in the second case, if we could visualize, we could see that our body heats up the air around it and that air rises. So this is a different mechanism than the one on the left. So in this chapter, we're going to study these two mechanisms, and also, most importantly, we would like to estimate how much heat are we losing and what are the factors, the parameters that define this heat loss. Examples of convective heat transfer is everywhere. It doesn't just relate to heat transfer from our body. So here are a few examples. So our indoor environment inside a room, so we may have a cooler and the cool air comes out from it would be dropping down because it's heavier, or we may have a heater where the hot air rises, so it sets up flow patterns and that determines how much heat transfer is going to take place. Now, we already talked about heat loss from our body that determines our thermal comfort. There are many industrial applications in the biological area of heating or cooling of liquids. One of the most important one is thermal sterilization or pasteurization to destroy bacteria in foods. So here, this can of liquid food would be heated sufficiently to sterilize the content, but because it's liquid, there's going to be flows happening and that will change the heat transfer. So we cannot do just conduction equations that we have done in the past. Now a little about the prerequisites for this chapter. So what you must know is the derivation of this transport equation, how this was derived, most importantly, what do each term represent. So to recap, it comes from conservation of energy. Okay, and in the past, we only kept this conduction term. We always dropped this term. This was dropped. Okay, but now in this chapter we have to keep it because this U stands for velocity and we're going to do heat transfer in fluid where the fluid is moving. So now we have to keep this term. Here we see how this chapter relates to other chapters in heat transfer. So chapter 3 was this general equation that we just talked about, and then 4, 5, 7 were the applications of that to steady state and unsteady state heat conduction. Now So that was all in solids and or fluids that are not moving. Now we want to apply this to fluids that are moving, so with bulk flow. And so we will restrict to steady state just to make our life easier. Unsteady state gets more complex. So we will talk about steady state heat transfer in fluids where the fluid is moving. So let's go over quickly the chapter learning outcomes. So we want to describe the process of convection heat transfer in a fluid in terms of what's called a boundary layer. And then explain convective heat transfer coefficient H that you are already familiar with. And identify the various types of flow and their effect on this convective heat transfer coefficient H. And finally, to be able to actually calculate the convective heat transfer coefficient H over a solid surface for various solid geometries, flow types, and fluid properties. Now, before we dive into the chapter, it is a good idea always to have an overview of what we're going to get out at the end. So unlike in the past when we talked about what goes on inside the solid, now it is outside the solid, the fluid over the solid surface is our interest. So this fluid could be colder, so which means heat could be transferring out from the surface of the solid. This is my surface of the solid, okay, and heat could be going out if the fluid is cold. This heat transfer is more complex situation than inside when it is just conduction. Okay, so here it is convection and it's more complex because of the flow. But we will describe this rate of heat transfer by this simple equation that you have already been using. But the question is, it's fine to describe it simply, but it has to be accurate. So what goes into this heat transfer coefficient? What makes up? What factors does it depend on? That's what is going to be our study. So this is what you will have at the end. You'll have an equation that looks like this or something, some other form where all you have to do is plug in the quantities like the velocity, or this is density or thermal conductivity to get H. So you might ask, if all we have to do is plug in these numbers or these quantities to get H, why don't I just give you? Why don't we just go over the formulas and be done with it, because we can all plug in. The trouble is there are many such formulas, and the formulas depend on the type of flow or the flow geometry and so on. So we have to really understand enough about the flow to be able to pick the right equation, for example. To use these equations appropriately, you have to know enough about the flow because they depend on the flow. That's what this chapter is about. Now, this slide is perhaps my most favorite slide. It also took a while to make this one, but most importantly, it really captures the main idea of convection in contrast with conduction. So if we have a hot surface here and a cold fluid here, okay, so the hot surface starts to heat up. So initially, like right then there is a large gradient between the surface and the fluid. So initially the gradient is very large, but the continuous transfer of heat, as you can see, the color red fills up the screen. It means everything is getting warmer and warmer. So as the fluid part, this is my surface, and the fluid part gets warmer and warmer, then the temperature difference between the surface and the fluid keeps dropping, or the gradient keeps dropping. Okay, so it starts off very high, but then it keeps dropping, and then until it settles on some very small value, which still keeps dropping, but maybe not as fast, but it's a much smaller value than it started. So now a rate of heat transfer is related to this gradient. So the rate of heat transfer, maybe it's very high initially here, but here it becomes low. So this is the problem with just conduction heat transfer. Now what will happen, can you think of, if I make the fluid move this way? What will happen, do you think? So all this part is just conduction, and at this point I'm going to make the fluid move, and then it will be convection, which is conduction that we already have, a plus flow. So as soon as we turn on the flow, the hot fluid here gets replaced by the colder fluid coming from the left. And what does that do? That maintains a gradient that is much higher, because it goes from hot to cold over a smaller distance. So the gradient is higher, gradient is increased, so the rate of heat transfer is increased. This is the central concept of convection over conduction. So convection, which is conduction plus flow, the flow basically helps to maintain a higher gradient and therefore higher rate of heat transfer over conduction. Now there are other types of convective heat transfer, not just over a surface. Here we have, for example, a hot plume rising, and of course that will also have heat transfer. This is a convective heat transfer as well, but we will not do this kind of situation simply because we have time limitations.